And we are live, and this is the TWIS Minion Science Island Hangout. And today you have the pleasure of listening to, watching two of the super brains of the internet. How's that for an introduction, Dale?
That's awesome. Super
I'd like
brain.
to see your TV station beat that. There you go. Popcorn.
I'm eating popcorn.
You're not going to see that on CNN, I'll tell you.
No. And I have a drink, too.
Oh, well, that's even better. And tonight we got some really interesting stories, interesting science news. And as I say, normally when I go through the articles, I can edit out some parts that are not particularly interesting and relevant. Can't do that tonight. All of our articles are just chock full of interesting information. We got a story about the quantum internet, not just a quantum computer, but the quantum internet. How our brain evaluates certainty in our choices. And an interesting aspect of that, and why I included it, is that, as Dale has said, if we're going to understand the brain, we have to approach it like we do software, like it's a machine. And that's what this does. We have a great article, a really great article by one of our Minions and sometimes Hangout participant, Amy Lynn, on Spaceflight Insider, talking about Curiosity detecting methane on Mars. Another Mars mission, Maven's on Mars, talking about, actually it's talking about a couple of different missions on Mars, identifying links to how Mars may have lost or is losing its atmosphere. Another really great advance, possibly, dengue fever, a real problem in many parts of the world. And these researchers have found an antibody which may lead to a vaccine. A couple of stories talking about different ways of looking at treating diseases. And researchers, they tend to focus on maybe the A part, which might be the virus, the bacteria, and maybe they focus on the B part, which is the human body. What we really got to look at is the interface. That's the critical part. Another article in Nature.com, which talks about a problem where when people will post, researchers will post their research work they've completed, and it has to be peer-reviewed. That's part of the process of science, but they don't always include enough information about the actual science behind it, the experiment part of it. And as a result, sometimes when other researchers try to replicate it as part of peer review, it doesn't work out properly. And got a couple of stories about how water may have first be on Earth and why we may have a lot more water under the Earth, under the deep crust of the Earth, than we ever thought we had. Now, all of this information, all of this fabulous stories and information, I mean, I don't have a brain that's big enough to deal with it. So what I need to collate and analyze all that information for me, what do you think, Dale? What do I need?
A quantum computer.
Yes, we need a quantum computer. Excellent segue into our first story.
So this first story, you got plans for a secure quantum internet and take a leap forward. You know, I'm not even sure what they mean by quantum internet, and I guess we're going to find out here as we go through this. Do you know what they're referring to?
No.
So I get quantum computer.
I guess the best thing would be to read the story, but one part of it, they're talking about using singularity as part of building a quantum computer, taking advantage of singularity and somehow applying that to constructing the internet.
Okay. Well, let's read through here. So we're saying the quantum internet has taken a leap forward. Scientists have created a device that can release a single, precisely shaped photon of light, opening the way to a secure quantum internet that is incredibly powerful and impenetrable to hackers. The vision is of a future network of quantum computers that can work together to solve problems beyond the capabilities of current machines. The key to developing a quantum internet is the ability to encode information on single photons of light that can be produced on demand. Now, Professor Andrea Fiore of Eindhoven University of Technology and colleagues have developed a nanoscale device that can do this by sculpting the shape of individual photons. This is a very important step to be able to produce single photons exactly when you want them. Quantum networks are highly sought after by governments around the world because they can make communication between two computers impenetrable to hackers. If someone does read the data while it's being transmitted, it is automatically changed, making the hack easily detectable. So the shape of a photon is determined by how smoothly the energy it contains is released. Most of the energy is released at the start of the process, with the remainder trailing off towards the end. Even though the emission takes just billionths of a second, it gives the photon a lopsided shape. Atoms naturally emit single photons, but these are not precise enough. Fiore and colleagues found that they could produce photons with controlled shapes using a quantum dot, a piece of semiconductor material that can emit a photon when triggered. To sculpt the photon, they placed the quantum dot inside a photonic crystal, which acted as a filter. In this situation, the emission depends on the energy of the quantum dot photon, which can be controlled by an applied voltage. This forces the light to escape at a steady pace. We have reported the discovery in the journal Nature Communications. Quantum computers, which are theoretically possible but have not yet been built successfully, work by exploiting the weirdness of quantum mechanics. Traditional computers hold their data in bits as either 1 or 0. These are manipulated by programs allowing the machine to arrive at the correct answer. Quantum computers hold this information in quantum bits, or qubits, that can be 1 and 0 simultaneously, a phenomena known as superposition. The calculation is encoded in the setup of the qubits, which can then perform all the calculations simultaneously, leading to a dramatic speed-up in performance. Dramatic's an understatement. This is radically different technology than we have today. It will make certain computational problems, such as forecasting the weather, much simpler to perform. At present, such calculations are carried out on supercomputers, but they still take too much time to do precisely, so approximations have to be made. Simulating the behavior of molecules would also be possible on a quantum computer, and this could help pharmaceutical companies design more effective drugs. The interrogation of big databases would also be dramatically speeded up. A quantum computer makes simultaneous calculations by synchronizing its qubits using a phenomenon called entanglement. This links the quantum properties of particles in a way that defies the classical laws of physics. For certain entangled states, measuring an entangled particle to learn its properties automatically forces its partner to assume the opposite characteristics. This happens instantaneously, no matter how far apart the two particles have been separated, something that Einstein called spooky action at a distance. So sharing entangled quantum data is not possible with current technology for transmission across today's internet. The precious qubits would have to be transformed into ordinary data, destroying their power. To make the most of quantum computers, you'll need a quantum internet. This new device is a step forward, sharing entangled particles, thus linking quantum computers across the world once they have been developed. These nanostructures can be integrated into devices and chips. It opens the way to the efficient exchange of photons between quantum chips, which could be used in a future quantum network. This is very good underpinning technology. A quantum internet is a real possibility, but it's not going to happen next week. To push the development of this technology, the UK government is investing £120 million in 4 quantum technology hubs. In November, the universities at Birmingham, Glasgow, Oxford, and York were announced as hub leaders by the Science Minister, Greg Clark. Interesting. So quantum internet is they're using entanglement. So when you change the spin of one particle, the other one spins right away, but they're not really detailed. Be really nice to look at the nature.
There is, sorry, in the chat area, just below where I put the article, it says abstract. Sorry, I didn't add that to where I listed the stories for you. That has more detail. I don't have the knowledge to interpret the information in the abstract, but that'll tell you. And when we post in the show notes, I will include the abstract for anyone who wants more detailed information.
Perfect. So in the abstract, okay, Nature Communications, they said dynamically controlling the emission of single excitons in photonic crystal cavities. So they're using a semiconductor, which basically means like a transistor is a type of semiconductor where you have a NPN junction, and semiconductor just refers to its physical properties, where they purposely dope the material lots of times at the atomic scale so that it doesn't conduct as efficiently. So you can bias, if you imagine, and this is what they're doing. So if you look at an NPN transistor, so you have N and P, or sorry, N with a P and an N. So you have the P sandwiched in between. So you have 2 N's on either side. And what they do is by modulating this P, by varying the voltage, for instance, or varying the current, you can affect how much actually goes through, and it could be turned on and off, or you can actually modulate how quickly the current is flowing through the transistor. So it could be an on-off state, or you could actually bias it in such a way that it makes energy flow freely. So they're using that semiconductor process to create and modulate these excitons. And in their abstract, they said single excitons, and I think that's the key, is they're able to send one at a time in semiconductor microcavities, represent a solid state and scalable platform for cavity quantum electrodynamics, potentially enabling an interface between flying and static quantum bits in the future quantum networks. While both single photon emission and the strong coupling regime has been demonstrated, further progress has been hampered by the inability to control the coherent evolution of the cavity quantum electrodynamic system in real time, as needed to produce and harness charge photon entanglement. Okay, so in order to get the perfect charge, which is required to achieve entanglement, what they've done with the semiconductor, I believe, is they're able to control the precise amount of charge to enable the release of a single photon. So they've made it perfect. I think before, when they were experimenting, it was more of an accident where they didn't have that ability to modulate it like that NPN junction on a conventional transistor. They did it in such a way that it was probably more accidental in nature, that they had a tough time. And this is all guesswork, but that's likely what happened. But with this breakthrough, now they'll be able to reliably do it every time. So if that's true, if that's what they're saying, and I'm understanding it correctly, this will affect every other lab doing this sort of research, because they'll be able to more predictably create the environment to do all sorts of new testing and move the whole technology forward.
Yeah, they say sharing entangled data is not possible with current technologies. For transmissions across today's internet, qubits would have to be transformed into ordinary data, destroying their power. So is it in this, they're going to have a cavity built into the chip, the qubit, and that's where these excitons will be in this cavity.
Well, I'm gonna, the best I can do is guess, and I think, I'm not a physicist, but what it sounds like to me is the cavity is within that semiconductor substrate.
Yeah.
And in that cavity, they're applying a very precise charge to that exciton, what will become an exciton. And once that happens, it will become in a state that's 0 and 1, so essentially a qubit. And they're able to send that one charged particle over a fiber transmission, because it's a photon, it's a type of photon, and it will be both 0 and 1 at the same time. So if somebody tries to read that data as it's passing from one side, from one point to another, if someone intercepts that data, we all know that, like if you have the cat in the box, it's neither dead or alive, but once you look at it or measure it, it changes state, and it settles on an answer. So that will make it so that they'll be able to detect instantly that that transmission medium has been hacked, because as soon as you measure it,
it changes. Okay.
It changes, yeah. So I think that's what they're saying, if that makes sense to you too.
Sort of makes sense. I mean, we would both need to be, I guess, computer physicist or something. But it's, I mean, even be able to, when they talk about sculpting a photon, wow. Controlling the charge, I guess, is what, of a photon.
Yeah, it's probably even beyond. It's probably controlling its charge and its spin state.
Yeah.
Because generally those charged particles will have a north and south pole, and you can derive its spin state via modulating it through this cavity. And modulating just means affecting it, right? So you're modulating it, you're affecting it, its charge state. And my suspicion is they're controlling the spin and giving it the precise charge where it will settle into a quantum state and not lose it won't decohere, which is always the problem in any sort of quantum system. Decoherence is when you have any sort of noisy environment and it loses its entanglement.
So if you have, let's say we have two computers interacting across the internet. Does this imply that the communication over the internet with these two computers, because of, we're talking about entanglement, is the entanglement the photon we're exciting in one chip on one computer interacting through entanglement instantaneously with another qubit on another computer, so that this is happening instantaneously?
I think that I don't know for sure, because did they, if I'm not mistaken, they referred to fiber, didn't they? Or am I just growing that out of my own head?
Fiber. I don't remember where they said.
Because if they didn't say fiber, I think you're right, Ed. I think where the beauty of entanglement is it doesn't matter how much space is separating the two entangled qubits, right? So maybe they just sit in these cavities, and as, so, but then that kind of makes me suspicious, because then why would you ever be, worried about somebody interfering in your transmission or being able to listen in, because that would be, I would think that would be physically impossible unless you had a transmission medium. And a transmission medium doesn't make a whole lot of sense in an entangled system.
Hmm. It might have said that, I don't know about the abstract. I don't see the, it says the nanostructure can be integrated into devices and chips. It opens the way to efficient exchange of photons between quantum chips. Well, let's see. No. One and two. No, I don't see where. I don't know. That's the impression I get.
I'm just kind of reading through the abstract a little bit.
I think the speeds at which information is transmitted over the internet is
when you create, right? When you create an entangled particle, you have to somehow create the entangled particles first, right? In order to do that, you have to smash the particle into two small particles, and every time you smash a particle like that, like through an accelerator or whatever you're doing, for a period of time, you have a qubit. But when you have those qubits that are entangled, or you have entanglement of these particles, I may be mixing up a whole bunch of different things here, but maybe you have to actually move one of those particles to its destination, and it will sit there, and it will communicate in an entangled state. But eventually, my understanding is that particles like that will have to have decoherence, and they'll fall apart, and you have to send a new particle in order to do it. Maybe that's what it is, or maybe I'm mixing my physics up. But we need some physics here.
Yeah, what it means is, you're going to have two quantum computers talking to each other, and having a server, that quantum computer in the cloud. So it is going to come down to creating that first quantum computer. Now they say one hasn't been created. I assume they're in the group that's saying that the D-Wave's computer isn't a quantum one. I don't know if that's true or not. I suspect you believe that that's less true, and that in fact D-Wave is creating a quantum computer. And
I'm hopeful. I'm hopeful.
Hopeful.
Right. It excites me that they may have something. There's a lot of really interesting investors that are backing it, and that gives it some credibility. I'm really hopeful that and I think this will be the year. We're going to find out.
That may be, hopefully, when we talk about predictions for next year, that might be the big story for next year. If D-Wave's quantum computer can act and can the way they believe it can, and that will become, that's what we can build our quantum internet, or whatever you want to call it, on. These D-Wave type quantum computers.
Yeah, my hope is that the adiabatic system that D-Wave is using, my understanding is it's not as flexible as the gate model. It's far less flexible, but it does some very interesting things, extremely interesting things that could help humanity propel us forward light years in so many different areas. But my understanding is it's not as flexible as the gate model. The problem with the gate model is it could be 30 to 100 years off. So I'll take that trade-off. If we have to have an adiabatic quantum computer that will help us cure cancer and help predict the weather, help us understand our environment, help us understand why the bees are dying. There's so many different things that it could help us with. Let's forget about the competition. If they have something, let's just get at the science and find out if it's real. Let's scrutinize this thing to death and if it doesn't survive scrutiny, let it go.
And it's becoming harder and harder to build technology, build machines that can observe the micro universe and the macro universe at the scale we need to improve our understanding. And so we need computers. We need quantum computers that can analyze data at the speed so that we can create these models that will do the observations for us. I don't know how. I mean, we can look inside. I mean, we can look at stem cells. We can look at how the stem cells are operating down at the molecular level. But now we're going to have to go beyond that. And I really think it's going to take that quantum computer to give us the ability to crunch the numbers and things that we need to make these dramatic leaps in understanding.
Right, yeah, like people don't, the average person, maybe they've heard the word quantum and they've heard the word quantum computer, and they think in terms of it being a lot faster. And that's a massive understatement. It just works in a completely different way. And for the type of problem that it's good at solving, if you look at the traveling salesman problem, finding the lowest energy states in a system, all things that help cure cancer, where a traditional supercomputer, if you took every supercomputer on the planet and tried to attempt to solve one of these problems, the issue is there isn't enough time that we'll have in the entire universe before all the suns explode and the universe collapses on itself. There will not be enough time to solve that problem, because the way a conventional computer works is zeros and ones, and it has to iterate through every single possibility. And in a chaotic system where things 2 becomes 4 becomes 8 becomes 16, you very quickly get into the billions. If you double a billion, it becomes 2 billion, 4 billion, 8 billion. It becomes trillions. Trillions double. As trillions double, you get into numbers that are unimaginable. And there is not enough time in our existence for our conventional supercomputers to solve these chaotic systems. But a quantum computer will tap on something very spooky that we don't completely understand, and the leading physical theory is parallel universes is what we're tapping on. And it almost embarrasses me to say that, but if you look at the physicists tell us, if you look at the data and the theory, that's the most plausible theory at the moment, is that we're tapping into parallel universes, and that's the horsepower behind these quantum systems. Seems crazy to me, but there's a lot of things that we found out that are extremely crazy that we went, oh, I guess it is true. And nature keeps surprising us.
Yeah, we really understand very little about how the universe works. And like I said, we're in kindergarten right now. And our ability to understand the universe like the physicists want to, boy, that requires being able to make observations way beyond our capability right now, way beyond it. And so that, our understanding kind of increases, our ability to make observations increases based on advances in technology. And that big advance in technology that's going to allow us to make these great leaps in understanding is going to be that quantum computer. So hopefully that will come next week. And I will mention to anybody who's watching, we have a question and answer mechanism. So you can actually ask us questions if you're in the Hangout, or if you're watching the Hangout, using the question and answer function. And we had, if I'm pronouncing it correctly, Solson.10 popped in for a second, and he actually used that function. It is working, and he hit the wrong link, but it is working, so you can ask us questions, and maybe we'll find the answer to your questions. I don't know.
At the very least, we'll have some fun talking about it.
Yes. And now I'm going to have some fun talking about how our brain makes decisions. And my goal, I want everybody in the world to make their decisions, to use a thought process. They want to think like a scientist. And this is the NYU, New York University Center for Neuroscience. In our daily lives, we make many decisions, says Rosba Kina, or something like that. Sorry, I'm mispronouncing your name. She's an assistant professor at NYU Center for Neuroscience. Sometimes the evidence afforded us is strong, enabling us to decide quickly and accurately. Other times the evidence is lacking, and we take longer to decide and tend to be less accurate. We can get back to that question. Our brain can learn that longer elapsed times are associated with lower accuracy and should mean less confidence. Our findings show that our brain used this association to calculate confidence, not just based on the available evidence, but also based on how long it takes to gather evidence. It's an intriguing notion that the brain might convert its data, there you go, brain and data, software, brain as software, gathered through the senses to units of degree of belief by combining evidence and elapsed time. And this is what co-author Michael Sheldon, who's a professor of neuroscience at Columbia University. These regularities that support the intuition that time might matter also made it, challenging to identify time itself as a player and not just a marker for something else, such as accuracy. It makes intuitive sense that time spent would serve as a clue about difficulty. Proving in the lab was not easy, though. It has been established that decisions are usually accompanied by a degree of certainty or confidence, a graded belief that our choices will produce positive outcomes. Confidence plays a critical role in guiding our future behavior in complex environments, especially when decision outcomes are delayed and rapid learning is required. Less understood, however, is how this certainty is established. Researchers have attributed it to a pair of variables, evidence and decision time. Specifically, if we believe we have sufficient evidence for making a decision, we are more likely to be certain in making that choice. When it comes to time, the quickness of a decision is seen as a reflection of confidence. The more rapidly we make a decision, the more confident we are in making it. However, it is challenging to separate these two factors, as the evidence supporting a specific choice typically affects the time we use to make it. To address this, the researchers designed an experiment in which the participants were asked to decide on the direction of motion, up or down, in a random dot motion display. Participants answered by making eye movement to either an up or down horizontal bar, directing their gaze towards one or the other end of the bar to indicate the level of confidence in that decision. The simultaneous expression of choice and confidence assured that participants were using the same information to guide both aspects of the question. The researchers controlled the level of difficulty, the noisiness of the motion, and tracked the eye movements to ascertain the choice, amount of time to make the choice, and the confidence in that choice. They say the results showed that more evidence boosted the confidence of the response. Moreover, certainty was inversely correlated with reaction time. In other words, the less time it took to make a decision, the more confident subjects felt about making their decisions. In a second experiment, the researchers disassociated the effect of time and evidence on confidence by manipulating the evidence, so that for a brief period, the net evidence was near zero. Subjects increased their decision times to achieve the same level of accuracy as before. Importantly, however, the reported confidence was lower, indicating that increased decision time can diminish the confidence even in the absence of appreciable changes in accuracy. And what they claim they showed, we showed for the first time that the relationship between decision time and confidence is not fully mediated by evidence. The elapsed time plays an independent role. In many situations, using the elapsed time is advantageous. It offers a computational shortcut and proves the reliability of calculated information. It also shows that we can disassociate accuracy and confidence by a manipulation that used in our experiment. Let's see. I'm also going to try to screen share. Come on, Internet. See, it's slow. It's redirecting slowly.
Yeah, mine is too.
Oh, right. Because it's because we don't have that quantum internet yet. Oh well, didn't work. They had a neat little diagram that showed how this worked. The longer the main thing is they're using experiments and even trying to create experiments to understand how our brain makes decisions. And really maybe the more important aspect of is the experiment itself. Creating an experiment that will help us see how our brain goes about making decisions. In this case, its confidence level with the time it takes for us to make a decision, and making a correlation perhaps between the time our brain takes to make the choice and saying that if it makes the choice quickly, there's a lot of confidence in that decision, and maybe that's a better decision.
Is that what they're saying? Is it does correlate? So a speedier decision equals a more accurate decision?
That's kind of what I was getting to it. That's not exactly what they were saying, however. If I could get that stupid diagram up, you could see a lot better what they were talking about. But
I couldn't get to the link. I tried getting to the link. I can't even get to the link.
Yeah.
It might be just that site.
Yeah. For all of you out there who will be watching this at some point, maybe the link will work for you, and then you'll see that wonderful diagram. I think the main thing here is, and this is the difficulty, we're talking about brain. how does the decision-making process of the brain work, and trying to design an experiment. And you really got to be able to look at it at the chemical level.
Yeah, for sure. And the deeper we go, the more chaotic the system gets, and the more we need a quantum computer.
Okay, why don't we go on to the next story? And this, Amy, if you're out there, 2 thumbs up, definite gold star. This is, I had read other reports about this story, talking about how Curiosity Rover had detected spikes in the Martian methane levels, but this particular article by Amy really showed that. There's really some great graphics, and man, I hope the screen share works. I'm going to try to screen share, and Dale, you can go on and read the story.
Okay. So this is from Amy, Spaceflight Insider. Curiosity rover detects spikes in Martian methane. Hints to life on the red planet.
Can you see the screen share?
Yeah, I can.
Great. Okay, go ahead. Sorry.
So this week is the annual fall meeting of the American Geophysical Union, a week of Earth and planetary science presentations where scientists, students, and media gather to hear the latest discoveries and developments. During a panel held Tuesday, December 16th, NASA revealed that its Mars Science Laboratory Curiosity rover has detected a hint of methane twice over the 20-month period. The findings, published in the journal Science, were discovered during 2 daytime sampling periods in late 2013 and early 2014. Scientists are unsure of the source that is producing the methane spikes and have not yet determined if the methane originated on Mars or arrived at the red planet via meteorites. Although organics such as methane can be present without the existence of life, this is the strongest evidence yet that Mars once supported life or might be doing so at present. We have full confidence that there is methane in the atmosphere of Mars, announced John Grotzinger of Caltech, a Curiosity Project scientist. Life is one of the few hypotheses for the formation of methane on Mars. And then there's a graphic showing methane abundance is on the left of that diagram, and the graphic shows a 10-fold spiking in the abundance of methane in the Martian atmosphere. Cool. So Curiosity landed on Mars 2 years ago in August 2012, and since its arrival, the Rolling Laboratory has been busy driving to Mount Sharp, an intriguing mountain located with Ancient Gale Crater. Along the path to this destination, Curiosity has collected samples at a few locations. The data received from Curiosity tells a lot about Mars' history and what the planet could have been like in the past. The methane detection is the first in situ, or on-site, detection of organics on the Martian surface. The data shows background levels of methane in the Martian atmosphere, as well as some episodic spikes that measure 7 parts per billion, roughly 10 times that of the background concentration. Wow, that's pretty small still, 7 parts per billion. So the results were described as an unexpected episodic increase in the Mars methane by members of the project. And what they said was a sudden spike, and just as suddenly as a disappearance of methane tells us that the Mars surface is communicating with the atmosphere. So they went on to say this temporary increase in methane, sharply up and then back down, tells us there must be some relatively localized source. There are many possible sources, biological or non-biological, such as interaction of water and rock. Why is this important? Organic molecules contain hydrogen and carbon, the building blocks of life. While the presence of these molecules does not definitively tell us if Mars supported life sometime in its history, we do know that Mars is chemically active and had conditions more favorable for life sometime in its past. We'll keep working on the puzzles these findings present. Can we learn more about the active chemistry causing such fluctuations in the amount of methane in the atmosphere? Can we choose rock targets where identifiable organics have been preserved? When Curiosity detected such a large spike in methane, one of the first things scientists did was work to determine if the methane was Martian in origin, or if it was produced as an unexpected side product by Curiosity's sample analysis at Mars' suite of instruments. Extensive testing analysis showed the methane was indeed Martian in origin. The amounts produced in the lab were nowhere near the amounts seen by Curiosity. So there's another graphic there. Whatever organic chemicals may be produced on Mars or delivered to Mars face several possible modes of being transformed or destroyed. So they show in the soil, they're showing organics, and due to the cosmic rays, I believe, surface with youngest cosmic ray exposure, erosion by, okay, wind-blown sand. So what they're saying, I think, is as the sand blows off the outer layers of the planet, any organics in the table would be destroyed due to the cosmic rays. So where you have the youngest cosmic ray exposure, there's a chance to detect organics with Curiosity. So identifying and detecting organics on Mars is complicated as the Martian rock and soil samples contain perchlorate. When the perchlorate is heated inside SAM, it reacts with the organics, ultimately changing the structure of the compounds. This process makes it virtually impossible for us to accurately identify which organic compounds we are seeing, an important distinction to make. So they noted organics are important because they can tell us about the chemical pathways by which they were formed and preserved. In turn, this is informative about Earth-Mars differences and whether or not particular environments represented by Gale Crater sedimentary rocks were more or less favorable for the accumulation of organic materials. The challenge now is to find other rocks on Mount Sharp that might have different and or more extensive inventories of organic compounds. Although the origin of the methane is currently unknown, there are three likely culprits. First, the alteration of the surface organics, meaning organics formed by ancient life on Mars that have been subsequently broken down by ultraviolet rays from the sun. Another possibility is the reaction of minerals, such as olivine, in Mars subsurface with water that create methane, a geological process known as serpentinization. Or the methane could have arrived via delivery service, like cosmic dust or micrometeorites. Regardless of how it was produced, the methane appears to have been stored in gas-like crystals in the Martian subsurface, known as clathrate hydrates. From time to time, the methane within the clathrates is disrupted and allowed to escape into the atmosphere. Based on the data received from Curiosity, the science team believes the source of the methane is close to Gale Crater. The stability of the clathrates depends on where are they are in the surface. Small impacts or thermal stresses may have destabilized the clathrates, which may represent ancient methane. They can be stored for billions of years. So another great graphic. They're showing the possibilities of how it might have got there. Underneath the graphic it says the Mars rover detected fluctuations in methane concentration in the atmosphere. So it says follow the water. There's water on Mars, but not like what is seen here on Earth. The water in and around Gale Crater appears to have been locked inside lakebed minerals some 3 billion years ago, with Curiosity getting its first taste of Martian water after drilling a sample of the Cumberland rock. With the help of SAM, scientists extracted and analyzed hydrogen isotopes within water molecules imprisoned in the rock. They determined the ratio of deuterium, a heavier hydrogen isotope with an added neutron, to normal hydrogen isotopes, providing a signature to compare across various stages of the planet's development. The ratio of deuterium to hydrogen varies across time because the lighter traditional hydrogen isotopes can escape into the upper atmosphere more easily than deuterium. To get a clear picture of how Mars water changes over time, scientists need to observe the current ratio of isotopes and compare that to the ratios discovered in rocks throughout the planet's development. It's really interesting that our measurements from Curiosity of gases extracted from ancient rocks can tell us about loss of water from Mars. So Curiosity drilled into a mudstone sample known as Cumberland and determined the deuterium to hydrogen ratio is in that sample is 1/2 the ratio detected in water vapor currently in the Martian atmosphere. This indicates that Mars has lost a significant amount of water since the formation of Cumberland rock. However, the Cumberland sample's ratio is 3 times higher than the ratio in Mars' original water supply, illustrating that the majority of water loss occurred before the Cumberland rock was formed. And another great chart. And it's the graphic showing the comparison between the amount of the organic chemical chlorobenzene detected in the Cumberland rock sample and amounts to the same compound in samples from 3 other Martian surface targets. Now what? Curiosity's science team is not sure when the next spike in methane will appear, but they will be monitoring the Martian surface closely in order to determine the source. Rottinger stated that over the coming months, Curiosity will drill more samples in an effort to try to identify the methane source trapped in the sediments. The team hypothesizes that the methane may originate from organic compounds built up over time in the Martian sediment, possibly even from billions of years ago, early on in Mars's history. While the detection of organics is not definitive proof of life we are searching for, it is the best evidence so far in favor of the possibility of life sometime in Martian history. Curiosity is turning the corner from a Star Trek exploration mode to boldly go where no one has gone before to a more deductive exploration mode. Curiosity is one element of NASA's ongoing Mars research and preparation for a human mission to Mars in the 2030s. Caltech manages the Jet Propulsion Laboratory in Pasadena, California, and JPL manages Curiosity Rover science investigations for NASA's Science Mission Directorate in Washington. Another fabulous article by Amy.
That's but that last graphic in particular. I mean, I read about Curiosity digging into the soil, and I say, okay, how much can they really learn? For as far as they're digging into it, well, you know what? They can learn a lot.
Yeah, I thought that was really interesting how the you know, when they cored into Cumberland, that the amount of water in the rock as compared to the atmosphere, they look at the ratio, and they know that at some point before that rock was formed, the amount of water vapor in the atmosphere had to be a lot higher.
Mm-hmm.
So I thought that was very sneaky of them.
That's amazing. It's how they can even perform that. That's not much reach. Yeah, that's how much science is being done right now. I mean, okay, we landed we had a robot on Mars, and it's rolling around, it's doing some stuff, but the amount of science that it's actually performing is much more than what I was expecting. And my next story is talking about an atmospheric let's see, what are we going to how Mars may have lost, may be losing its atmosphere. Let me just quickly check. I'll do a quick screen share, simply so that when I'm talking you don't have to look at the top of my head. All right. And this is NASA's MAVEN mission. And early discoveries by NASA's newest Mars orbiter are starting to reveal key features about the loss of the planet's atmosphere to space over time. The findings are among the first returns from NASA's Mars Atmospheric and Volatile Evolution mission, MAVEN, which entered its science phase on November 16th. The observations reveal a new process by which the solar wind can penetrate deep into a planetary atmosphere. They include the first comprehensive measurements of the composition of Mars's upper atmosphere and electronically charged ionosphere. The results also offer an unprecedented view of the ions as they gain the energy that will lead to their escape from the atmosphere. We're beginning to see the links in a chain that begins with solar-driven processes acting on gas in the upper atmosphere and leads to atmospheric loss. And this is Bruce Jakowski. Mispronounced his name, I'm sure, but he's the principal investigator with the Laboratory for Atmospheric and Space Physics at the University of Colorado in Boulder. Over the course of the full mission, we will be able to fill this picture and really understand the processes by which the atmosphere changed over time. And that is amazing. On each, this kind of information we're only getting it for maybe the last 5 years or so since we've been putting these satellites up here. And you can just imagine how much more we're going to learn. In each orbit around Mars, MAVEN dips into the ionosphere, the layer of ions and electrons extending from about 70 to 300 miles above the surface. This layer serves as a kind of shield around the planet, deflecting the solar wind, an intense storm of high energy particles from the sun. Scientists have long thought that measurements of the solar wind could be made only before these particles hit the invisible boundary of the ionosphere. MAVEN's solar wind ion analyzer, however, has discovered a stream of solar wind particles that are not deflected but penetrate deep into Mars's upper atmosphere and ionosphere. Interactions in the upper atmosphere appear to transform this stream of ions into a neutral form that can penetrate into surprisingly low altitudes. Deep in the ionosphere, the stream emerges in ion form again. The reappearance of these ions, which retain characteristics of the pristine solar wind, provides a new way to track the properties of the solar wind and may make it easier to link drivers of atmospheric loss directly to activity in the upper atmosphere and ionosphere. MAVEN's natural gas and ion mass spectrometer is exploring the nature of the reservoir from which gases are escaping by conducting the first comprehensive analysis of the composition of the upper atmosphere and ionosphere. These studies will help researchers make connections between the lower atmosphere, which controls climate, and the upper atmosphere where the loss is occurring. The instrument has measured the abundance of many phases in ion and neutral forms, revealing well-defined structure in the upper atmosphere and ionosphere, in contrast to the lower atmosphere where gases are well mixed. The variations in this abundance over time provide new insight into the physics and chemistry of this region, and have already provided evidence of significant upper atmospheric weather that has not been measured in detail before. The new insight into how gases leave the atmosphere is being provided by the spacecraft's super thermal and thermal ion composition instruments. Within hours after being turned on in Mars, static detected the polar plume of ions escaping from Mars. This measurement is important in determining the rate of atmospheric loss. As the satellite dips down into the atmosphere, static identifies the cold ionosphere at closest approach and subsequently measures the heating of this charged gas to escape philosophies, well, whatever. Sorry. As Maven raises in altitude. The energized ions ultimately break free of the planet's gravity as they move along a plume that extends beyond Mars. And I'll stop there. So more measurements on Mars.
So, okay, they're doing all this science to basically get there with humans at some point. They're trying to learn as much as they can. I think that's the end goal. And at some point, technology will probably come down in price due to innovation, and that will somewhere meet with the politics, world politics, and their appetite to go, and we'll actually get there. So my question is, on that point, when we hit that sweet spot, are you going to go, Ed?
I'm going to go if we go underground. I'm not going if it's going to be above ground. Now, how far underground? Because that, actually, this article talking about the ionosphere and how far it's getting into the surface itself, that's an important question. So my thinking is trying to create habitats above ground, that's going to be very problematical. So I think it might be better to create habitats underground, do the experimentations, etc., above ground, do exploring and things above ground, but spend the most of your time, the largest percent of the time that you spend on Mars, do it below ground where it will be safer.
So with all these, the increased radiation exposure on the trip, the 6 months and everything else, they say it would be equivalent to being a pilot, because pilots are exposed to more radiation being in the air. The estimate I've heard is that the 6-month mission, you would take on the same amount of radiation as you'd get from being a pilot for their entire career, for like a 40-year career. So you get that much, and what they say is, if you're a smoker and you have a 20% increase in the chance of lung cancer, basically what they said is you'd add 1 more percent to that risk factor, and that's the radiation. So now that comes from one of the, I forget the guy's name, but it's the one that proposed the mission that NASA was very happy about. They presented their proposal, how to get there, and it was received quite well. So you never know who to believe. That doesn't sound like a lot of radiation when you put it in perspective. So would I want to go there and live there, one-way trip? I don't know. It sounds good for maybe a few weeks, but I think you'd get there, and after being there for a couple of weeks, there's no movie theater close by.
Well, don't forget, in my scenario, if I'm in charge of the space missions, I'm starting with, when it comes to habitat, I'm starting with the moon. And we can get back and forth to the moon pretty quickly, 3 days or so. So you can operate just like you do with the space station, International Space Station. You only spend X amount of time being exposed to that level of radiation. And then by the time you reach the point, and you perfect things, and maybe what you want to have even with you is some way of, I don't know if it's decontamination, or some way, or maybe even evolution, evolving so that we can deal with all that radiation, or some way of when you get on the moon and when you ultimately get on Mars, you're treated in some way so you can get back to a normal, healthy state.
Well, radiation, my understanding is, like, the damage it does is it's messing with your DNA and your RNA. So maybe if they perfect CRISPR-Cas9, we just reprogram ourselves from those mutations, and that's it. I think that's where we're headed. I really do.
Now, I mean, I want to stay on Earth. If they said we've got that Mars trip, sign up and you're going to be there, and you plan maybe 5 years. 5 years you're going to be there on Mars. That I would not sign up for. But if I'm here and I see progress not being made, the atmosphere being more polluted, etc., I don't know, maybe that might swing the decision a little bit more. And eventually, and we've talked about this, once we get that AI intelligence, that quantum computer, supercomputer intelligence, we humans, we don't have to do any work or anything. We're going to have the two choices. Like you, we can become a craftsman, a musician perhaps, an artist, or the other occupation is going to be exploring space, Mars being the first step, and beyond. So the occupations are going to be artistic, crafty, or space missions. In that scenario, I'm hopping on that spaceship.
Well, I think a lot of the, like, read an article just recently, a few days ago, I believe it was Forbes, and they discussed that they believe that this year will be the first year that artificial intelligence will be replacing human beings on a large scale. So where you have call centers with tons of people, the AI is going to be strong enough where they're doing away with human workers and replacing it with AI. And so that's coming right away. That worries me a little bit. Where will those workers go? What will they do? I know in the past we've had things where, if you look at 1991 and you think of, wow, this internet thing is coming and it's scary. It's going to make so much, we're going to lose all of our buildings. Nobody will go to a mall anymore, so we're going to lose our brick and mortar shops. It didn't happen, and lots of jobs were lost, but all of a sudden new jobs were created, like web developers, all sorts of interesting new occupations were created and generated from that. My hope is what's to come is a lot of occupations will be generated, and it won't be just purely the AIs that will take over all of that sort of thing. So if that happens, if the AIs do get strong enough that isn't very much work, there's some question marks there that I'm concerned about.
It's the pace of change, and that's something we've worried about and people have talked about. Every time there's a new advance, a quantum leap in technology, going from the horse and buggy to the car, the pace of change might well is picking up. How much is picking up is the question. Are we adapting? Are we making the steps to adapt to change as quickly as we need to? That's a good question. We have a lot of problems in the work environment right now, in the short term, certainly in the United States, where you have a lot of people, middle-class people, who may not have or are not getting the training to perform the jobs that will be created 5 years from now. I don't know. Are we training people quickly enough so that the jobs that do get created, well, I'll say 10 years, not 5 years, but 10 years. I don't know. Education is going to be the key.
I don't know. I have trouble with that too, because that's always been this sort of factor. Going backwards in time, it's always been about the education, and it's always been true. But this next change that's going to occur is about intelligent synthetic life that's, way beyond our capability to learn. Is, why do we need it? We phased out all sorts of technology in the past. We phased out many things because the computers can just do it automatically. We don't have to count by hand anymore. So I worry about that. I think where the jobs will be is where the computers can't be. And yeah, there will be some things in for instance, AI development and integration between technologies. I think there will be a lot of integration type jobs where, okay, there's AIs out there that are intelligent like Watson. I work in broadcasting, so how do you integrate the AI technology into broadcasting? I think there will be all sorts of integration possibilities that never existed. But then there will be, for the worker that doesn't have a lot of knowledge-based intellect, they'll be able to do other things where more basic things, which is great. Like, okay, I go out and climb towers. An AI in the near term isn't going to be climbing a tower to do maintenance, and there are hundreds of thousands of towers, right? So there will be things, I think a person has to almost, there are intellectual and non-intellectual jobs that will be functional, and you just have to think about realistically, what can an AI do for us? And if you're one of those persons that is not university educated and doesn't have a degree in something that's going to be, not replaced, then you've got to look at something practical that robotics can't take over warehouses. For the most part, they're going to take they're already taking on a big role, AIs and robotics. You need to do something that they can't do, and tower maintenance is a good example of a physical job that an AI won't replace anytime soon, I don't think.
Well, the first thing is education, and we will have a change in how we educate ourselves and our children, and it will be mostly online. We won't be going to universities and spending 4 years getting a degree. We won't be going on to PhDs. We're going to be getting information. We're going to be going online, and we're going to be controlling our own educational process, learning at as fast a pace as we can. So many more people who right now may not think of themselves as having the knowledge to be able to become a programmer or something, they have the brain power to do it. And once they're able to control their learning process, they will learn at a much faster rate. And at least for the short term, what that will mean is more people creating their own programs, their own apps for cell phones and smartphones and whatever. You're going to see people, what's the term I'm thinking of? Independent. People working independently, perhaps. If you're at a corporation, well, the corporation has a goal of making money. It makes money by having products. And then 96 people around the United States in their homes will be designing them or whatever, creating programs or whatever it happens to be. And they'll be able to do that on their own. And if they want to put in 20 hours a day doing it, they'll put in 20 hours a day doing it. And so the design process, I think that's where you'll see more jobs for people, at least initially. But I'm thinking 5, 10 years. I don't think that AI intelligence is going to be taking over quite as quickly. The AI intelligence for the next 5 or 10 years is going to be helping us. Story last week where you had a 94-year-old woman, and she had a computer that was on a little robot stand that could move around the house, and her son could watch her and help her. So she could live in her own home because she had that robot assistant. So I think that's the kind of like doing surgery. At least for the next 5 years or so, we're still going to need that human being controlling the surgery. We're still going to need that human doctor analyzing the results and making recommendations to you. 10, 15, 20 years down the road, that's not going to be the case. And then I don't know. That's where I don't know.
Yeah, and I just hope that, like, anytime technology has created abundance for ourselves, right? And an example being, you know, the creation of making abundant aluminum. You know, before it was created, it was more valuable than gold. Before they came up with a process, pre-industrialized process that basically made aluminum commonplace. Before that, it was unaffordable. No one could access it. No one could use it because in its natural state, it was extremely difficult to come into. So anytime you have technology making it simple and cheap and available, it becomes abundant, and we all get it for next to nothing. So we're hitting a point where technologies, and you know, this is a lot from Diamandis, right? He talks about abundance. That's his whole shtick is abundance, and I'm a believer in Diamandis. He's part of the X Prize Foundation. I just worry about that interchange. I really worry about, before we get there, we are headed towards a zero marginal cost. So the cost of things, I think, will keep coming down. And I just looked at an analytical trend of flight. And if you look at what it cost in the 1980s for flight, and you compare it in relative terms to today, more people are flying. It's where it was, you know, you were lucky to fly a couple times in your life. It's become a thing where, yeah, going to Mexico for holidays. I'm flying to Europe for 3 or 4 days. That's become more commonplace. Only because the costs have dropped, and that's through technological abundance that it's provided. So even though the cost is getting cheaper and cheaper, we still have to work to make some sort of money to be able to pay for that cost. So to get from here to there, I worry about the next 30 to 40 years, I guess, is the time frame I'm concerned about. I think after that, if we've made it, we'll hit that Star Trek type perfect society where power won't matter because everything will be provided. And I know that sounds kind of kooky, but if you look at the data tends to move in that direction if you follow it. So I guess we'll see. Maybe it will be kooky, and that's if I know anything about predictions, it's that most of them are usually wrong.
Before we go on to the next story, I can add a couple of points. The first is, anywhere you are humans who prefer to interact with humans, and they're in jobs that involve that human-to-human interaction. I don't know if it's getting a massage or whatever the heck it is, but there's still going to be a lot of jobs where we're going to prefer to deal with a human being instead of a robot. Number two, the robots will need us for something. We're going to have collaboration type work, I don't know what kind, between robots and humans working side by side, and the human will be able to provide something, I don't know what, something that the robot will see as valuable. So we will be of value to these robots. And the last point is, okay, we have a problem, we're worried about artificial intelligence. Who do you want to deal with? Do you want to deal with the Islamic State? Or do you want to deal with an artificial intelligence? Do you want to deal with Adolf Hitler? Or do you want to deal with artificial intelligence? I kind of think I'd rather deal with artificial intelligence.
I guess
and here's the man joining us right now, Jani. who's a huge fan of artificial intelligence. Go ahead, Dan.
I agree with all that. I think that the undercurrent to this whole conversation is it doesn't matter. It's AI is coming, whether we like it or not. So we better get our heads around it, and we better talk about it. And I'm going to make a prediction. I think that when we're having this hangout next year before Christmas, a year from today, I think what we're going to see in lots of industries, and I'll use healthcare as an example, the unions will be upset and extremely concerned with platforms like Watson. And there will be at least 2 other platforms out there besides IBM that are beginning to float a commercial product to basically have an impact on the people resources needed within healthcare. And I think when we have this conversation next year, we're going to see the AIs have gotten to the point where it may not be mainstream media, but we'll hear enough about from the unions and everything else that they're going to be concerned about it. I think if we go another year to 2 years in advance, I think that slight worry is going to change into mainstream media articles where the unions are completely enraged over the possibility, and they will ultimately lose, whether it's healthcare or whatever. People will go with cost efficiency. And I don't know if that's good, bad, or otherwise, but that's my prediction.
Yeah, but first of all, in the United States, the unions don't really have much power anymore. And
I use it as a barometer, though. Like I'm thinking of them as a barometer, and it'll be an indicator that the average person in a union will begin to flag artificial intelligence. Because right now, they probably don't even see it as a threat. I think a year from now, they'll begin to perceive it as, oh no, I've seen Watson or I've heard of Watson, and I'm beginning to worry about my job. I think that barometer is the most important thing.
I'm going to disagree with you. I'm going to say the benefits that we will see will make us collectively more optimistic about a future with artificial intelligence.
I agree. I just think if you're working within healthcare, you're going to be worried.
There are professions you're going to be worried about, but there's plenty of work. For instance, in the United States, right now, we have a problem with an aging infrastructure. There is tons of work for people like Ulysses Aikens. You know, there's tons of work on the roads, the bridges, whatever, and on the infrastructure itself. Tons of jobs, potential jobs available. And sooner or later, the infrastructure is going to fall apart before we get that AI, robot that can do the job. So I think there's a potential for enormous amount for the unemployment rate to really drop down. So I'm very optimistic in terms of workers. The scientific community, I'm not. I think even within the scientific community, where AI might be the bigger threat, or doctors where AI, maybe the doctor can see that AI being a bigger threat, but still the benefits they're going to be gaining during the short term in terms of diagnosis of illness, in terms of coming up with better treatments, the benefits are going to outweigh any concerns about the long run. But it's, there's going to be a point. But I think that point isn't going to be next year. I think that point will be more like 10 years down the road. I think for the next 10 years, for the next 5 years, I'm worried about the world and the country for different reasons.
Okay, and I think within 2 years...
But I'm optimistic about 5 to 10 years, and 10 years down the road, very optimistic we'll figure it out.
I'm very optimistic about everything, but I think there's these trouble spots. And I think within 2 years, Apple, the new sensors that are coming out on the phones, see, in order for them to make more money and not have all these competitors, right, that are now making the same product as Apple, like say an iPhone, the only way they can keep their price high on those specific products is to add sensors. And as you add new types of sensors to these phones, people will create new apps. And that will allow them to keep the price point high. The market is getting flooded with similar products that are lower in cost, and that drives down the cost of what they'll be able to charge unless they add more sensors. And I think health is the way forward. And within 2 years, there's going to be sensors on your iPhone that will eliminate the need to see a doctor except for the very, very unusual time when it's a case of trauma, or when your doctor says, I looked at your results and your data that came off your iPhone, I need you to come in so I can chat with you. I think that's very close.
Yeah, once you go chat with your daughter, she's probably very concerned. Yeah. She's been listening to you talk, and she's probably very concerned now about her future.
Oh, yeah.
How you doing, Yanni?
Good.
That's good.
I think we kind of say the same thing.
Okay, let us move on to the next story. Let's see. We're probably not going to get to all the stories tonight. I doubt it, which is fine. But each one of these, man, there's so much amazing, interesting news. So why don't you talk about what some researchers have learned about dengue fever and the possibility of a vaccine.
So dengue fever vaccine on the cards after novel antibody discovery. So the antibodies could be used to treat dengue fever or develop a vaccine that works against all 4 strains of the virus. So a new class of antibody found in the blood of patients with dengue fever has boosted hopes for a vaccine against the virus, which debilitates millions and kills tens of thousands each year. Cases of dengue fever have soared in the past 50 years to nearly 100 million a year, as improved transport and urbanization have brought more people into contact with the mosquito-borne virus. And just kind of falling back to that last story, if they solve something like this, you immediately need a lot less healthcare workers. All right, so the case of dengue fever soared in the past 50 years, and it's basically transmitted through like mosquitoes, that sort of thing. While dengue infection often causes mild to high fever and lasts only a week or so, some patients develop dengue hemorrhagic fever, which is far more serious and kills about 22,000 people a year, many of them children. The real problem with dengue is it occurs in an epidemic fashion, so it can paralyze healthcare systems when it comes through a big city, causing thousands of hospitalizations. It's likely that without a vaccine, this disease is not going to be controlled. The researchers spotted the new group of antibodies while they were studying blood drawn from patients who picked up dengue infections in Southeast Asia. They found that about a third of the immune reaction launched by each patient came from a new class of antibodies. Instead of latching onto a single protein on the virus surface, as usually happens, the new group of antibodies latches onto a molecular bridge that joins 2 virus proteins together. When antibodies bind to viruses, they make them targets for attack for the wider immune system. In tests described in the journal Nature Immunology, the researchers found that the newly identified antibodies were highly effective at fighting the dengue virus in mosquitoes and in patients. But more surprising and useful for a vaccine, they also neutralized all the different forms of the germ. There are 4 different strains of dengue virus. When a person becomes infected, their body will become immune to that strain, but they're still vulnerable to infection from the other 3. Reinfection with the second strain of dengue substantially raises the risk of developing serious dengue hemorrhagic fever. The antibodies were effective against all 4 strains of this virus because they all share the molecular bridge the antibodies attach to. So in follow-up work reported in the study, the scientists went on to manufacture a batch of human antibodies. Once they have cleared trials, this could be used to treat dengue fever or administered to protect people against the virus. But another approach is to synthesize the virus's molecular bridge in a form that it can itself be used in a vaccine. Such a vaccine would protect against the infection by training the immune system to recognize the bridge and so attack any virus as soon as it enters the body. About 2.5 billion people, more than a third of the world's population, live in areas where dengue infection is a risk. The virus is endemic in at least 100 countries in the Americas, Africa, Asia, and the Pacific and Caribbean. That sounds really promising.
Mm-hmm.
So yeah, if they're targeting the bridge that bridge the two dengue proteins together, and because it's hitting the bridge itself, it'll basically go after all 4 strains of the virus, which is wonderful. So it's actually fortunate that it has this common bridge that will basically be an effective antibody attaching to all the different proteins that it needs to attach to.
That's a problem. The dengue fever has not been a good target for vaccines in the past. And the problem is you have people who get infected with one strain and they survive. But once you've been infected with one strain, if you're reinfected by that second strain, then your chances of survival decrease. So these people live in an environment where there's a good chance they're going to get reinfected. So you really need that vaccine that can deal with all 4 of the strains. And one thing I think they mentioned here, they say without a vaccine, it's really, really difficult to deal with that disease because there's 4 different strains.
Yeah. Yeah, it's like you're dealing with 4 different pathogens.
Mm-hmm.
So, awesome.
I've got, let's see, 2 stories. Now the articles talking about the stories are very long. So I guess my question is, Dale, how much longer can you stay with this past 12 o'clock? I mean, going through one of these are 4 or 5 page news, and everybody out there, they're going to be in the show notes so you can read about it. But for the purpose of our discussion, if you could look at these 2, you can pick one, and we'll just go over one, and that's going to take us, I think, till 12 o'clock.
Okay. Well, let's pick one then. Like we've got the
5 and 6. No, 6 and 7.
6 and 7. That one really interests me, and they want to ditch the term pathogen.
Yes, I like. Yes, that's interesting, and that's also because it deals with it. The main point of their story is that in attacking disease, you have A, which is the disease itself, and then you have B, the human, and the focus is on either A, or there tends to be a focus on either A or B, but the important thing is the interaction. That's the important thing, and that's what they're talking about here. Instead of the pathogen itself, you know, it doesn't help you that much to understand the pathogen and then also understand the human. You've got to understand the interaction, and I'm going to be reading for a while. I mean, there's really a lot of interesting information in this particular article. And this is from Nature.com. And this is an article by Arturo Casadevall and Lisa Ann Porofsky. The term pathogen started to be used in the 1880s to mean a microbe that can cause disease. Ever since, scientists have been searching for properties in bacteria, fungi, viruses, and parasites that account for their ability to make us ill. Some seminal discoveries have resulted, such as the roles of various bacteria and fungi toxins in disease. Instead, our oldest and most reliable vaccines, such as those for diphtheria and tetanus, work by prompting the body to produce antibodies that neutralize bacteria toxins. Yet a microbe cannot cause disease without a host. What actually kills people with diphtheria, for example, is the strong inflammatory response that the diphtheria toxin triggers. Likewise, it is the massive activation of white blood cells that triggered by certain strains of I can't pronounce the difference between these two words, so I'll go with streptococcus bacteria, that can lead to toxic shock syndrome. Disease is one of several outcomes of an interaction between a host and a microbe. That sounds obvious, spelled out that way, but the issue here is more than just semantics. The use of the term pathogen sustains an unhelpful focus among researchers and clinicians on microbes that could be hindering the discovery of treatments. In the current Ebola epidemic in West Africa, for instance, much attention has been focused on the ill and the dead, even though critical clues to curing the outbreak may be found in those who have remained healthy despite being exposed to the virus. Instead of focusing on what microbes do or don't, researchers should ask whether an interaction between a host and a microbe damages the host, and if so, how. This approach will require different tools and potentially more alliances between microbiologists and immunologists. And my voice is not going to be able to carry us through, so I am going to jump ahead a little bit. I'm going to jump ahead to the end. The term pathogen is unlikely to go away, but those who study the infectious diseases need to own up to its limitations. Researchers probing the human microbiome, the community of microorganisms that live in and on our bodies, using genomics, are being forced to recognize that myriad factors and interactions shape its composition. It varies in different people at different times in development and in association with disease. Yet much of the research on infectious diseases continues to be dominated by reductionist approaches. One variable is altered while all others are assumed to be constant. Microbiologists tend to view the microbe as the key variable in disease and treat the host as a constant. Immunologists generally see the microbe as a constant and the host response as the variable. For instance, immunologists frequently inject microbes into normal and genetically manipulated laboratory animals to assess the factors that shape the host response. These two groups go to different conferences, read and publish in different journals, and receive funds from different granting panels. What is needed is a simultaneous analysis of microbial and host variables using new analytical tools. Damage to the host is a measurable parameter that can result from the microbes, the host response, or both, and as such, it shifts the focus onto the host-microbe interaction. New tools are needed to measure the spectrum of inflammatory, biochemical, and other forms of damage resulting from the interaction between the host and the microbes. The discovery and development of these tools must be driven by new sessions at conferences, special issues of journals, and dedicating funding streams. We think that such a shift in approach would uncover all sorts of possibilities for preventing infectious diseases. Now, I did jump ahead, and in the middle they give a lot more examples to support their argument. But
All right, so I have a comment for this. So I think they're right where they're saying to look at the microbe in real time in vivo in live human beings and see how it's reacting with the human subject, right?
Hmm.
I believe that, but I want to take that even a step further, where what they're saying is to use the word pathogen, for instance, is referring to an old time when we didn't completely understand what was going on in the body, and it helped us along for a period of time. But a pathogen now has all sorts of vectors. It's not as simple as one thing affecting another. So I'm going to coin something, and I'm going to invent a new word. And
Ooh, new word.
it is a new word, and I think scientists should start to use it. Instead of a pathogen, they should refer to it as pathomic, right? Because
Pathogen. Okay.
pathomic, because a pathogen refers to the pathology, right, which
Hmm.
is how it's reacting in whatever species you're examining. And the omic part refers to all the multiple types of genomic type institutions there are now. There's metabolomics. There's all sorts of different omics with it
Hmm.
behind it, and it depends what you're studying. And it's because we've been able to sequence things that all these different new types of omics sciences exist. So I think pathomic um, should refer to the chaotic nature of all these different disciplines interacting with each other. And I'd go beyond just saying that the microbe and how it interfaces with the human subject. It's even more than that. It's
Hmm.
how everything is functioning in a chaotic system. And again, the end game there goes back to big data and our ability to interpret big data from these different scientific disciplines within biology. Pathomic, pathomic, pathomic.
Pathogen.
Let's see if that spreads.
There we go. That's how we can make money. New words, inventing new words. Let's see, Yanni in the chat room. We could get health data from different sensors already, but it just needs to get across to more openly, like the system notifying patient health to smart devices. And that's exactly what we've been talking about, Yanni. You have that wearable device. And we're not that far away. That we're not too far away from. For instance, I'm a diabetic. I have a machine that takes a little blood sample. I can take that blood sample, put it on my little wearable device. The wearable device does the analysis. Boom, goes out to my doctor, the quantum computer, whatever, does the analysis. And it's like you said, the sensors in these devices are going to dramatically improve. So,
Is the key there, Yanni, in your sentence, you use the word openly? Are you referring to like open source, where the only way this is going to be effective is if it's open sourced? Is that what you mean?
No, just open source.
Oh, so you mean open source is the critical component. And I agree. If we have all these islands of
oh, okay.
technology,
Now I see what you mean.
yeah, if we have all these islands of technology that's not easily shareable, and I think where this will come from is the same crowd that does Wikipedia and anybody working in the open source movement, and that's getting more powerful as we go. But it comes down to someone like us basically making it a reality and getting other people interested and making it happen. And sometimes we all tend to look outwardly to, where's that expert that's going to create this? And many times I find the expert is the one that you're looking at in the mirror. And sometimes we don't think of ourselves in that way, but I think the open source movement is one of those movements where it's all comes from within. So I think he's right. We have to um, make it so that these different systems have to play along with each other.
Yeah, and that's Open source, I wonder if it's inevitable. For instance, now we have the copyright business. But now, you have NASA. NASA has all its research strictly open source. You even have a page, an online page you can go to. You can look at all their different, I can't think of the right word, but all the research that they've done on different things. It's all there. It's all open for anybody to use. Now, if you're not open, and you try to say, we're going to go into this nice little closed environment, you're going to get hacked anyway. So it's going to be open. It's going to get out there one way or the other.
Well, that sparks something in my mind. I think the closer we get to products that are near zero marginal cost, if you were able to put that on a plot, inversely proportional will be the amount of open source movement. Because as profit matters less, the open source movement and participation there will increase, I think, and they'll be inversely proportional.
Mm-hmm. Yeah.
Let's hope, anyways.
I think openness, or more openness, is inevitable. It will happen. There's still a lot of pushback. Even colleges have copyrighted some of the research, and so there is a focus on monetizing. You've done all the work on this thing. You want to monetize it as much as possible. And if somebody else tries to copy and use it, you sue the pants off them.
And it's because the profit matters a lot,
yes,
and that market matters.
That's going to be less and less.
Yeah, yes. And I think it will be less and less. I think we're living it right now. We just can't see it because we can't see outside our, 3 to 5 year, linear bubble that we all ride in.
Yeah, that's just like music is changing. So you had the model where a company controlled the music, and if you were a performer, you went to that company, and then you signed a contract, and they controlled how that particular song or whatever it is got distributed, and they collected a lion's share of the money, etc. That model is broken. Anybody can go online. You now have people going online, coming up with a song or something, getting millions of followers, and the next thing you know, somebody's signing them to a record contract. Or they can monetize that themselves. They don't need a distributor. And you're seeing that in even movies, television, the individual, the YouTube, going on to YouTube and creating their own. Openness. Openness is the future, the wave of the future.
Yeah, technology has a way of creating abundance and vaporizing old sort of linear monoliths.
Yeah. I'm going to, my voice is beginning to go a little bit. We're approaching the 12, for me, I guess almost 2 hours we've been in here. But one thing I'll mention is that this will be the last Hangout probably of the year. We'll be seeing each other next in the Hangout like this probably in 2015. Hopefully shortly thereafter, D-Wave will come out with that quantum computer. So I want to wish everybody a happy holidays, whatever holidays you celebrate. I'm going to be spending my Christmas, unfortunately, in a toxoplasma gondii environment with my cousin and her 6 cats.
Awesome.
What are you going to be doing, Dale?
Not too much.
Too much?
No, not too much. Just relaxing, spending
That's
time
good.
with family and friends. So it should be really good. I was kind of hoping, maybe when you back, so you're going away for your vacation?
Oh no, I'm not going. I'm going away on Christmas Day.
Oh, okay.
Vacation? I'm retired. Every day's a vacation.
That's awesome. Well, in the new year, one thing that I want to do is, from a technology standpoint, which is the technologies we have are simply applied science. I want to do a live hangout from the top of a tower.
Ooh, that'd be exciting.
So we'll do that Google Hangout when it gets warm, and so next year, I think that'd be fun to talk about coaxing electrons up a transmission medium and how it propagates and measure it in real time, and actually do a little bit of a science experiment as we get some warmer weather in spring.
You will have some people underneath you, however, in case. Here's the experiment. Watch electrons flow, grabbing the cord.
That's right. Yeah. Yeah. No, I think that would be a lot of fun to see something, some application of something.
Boy, I tell you, this year, with these Hangouts, two things have been advancing my science education better than at any point in my life. The This Week in Science podcast and these Hangouts.
Oh, for sure. Absolutely. They're fun.
It's been great having you.
Yeah, I really enjoy it.
One thing I'm gonna end with, and I know Jani's celebrating Christmas in Finland, and there's a festival that I saw. So I'm gonna screen share a YouTube video of a very beautiful holiday festival, St. Lucia's Day. It was celebrated on the 13th. I think it's also celebrated in Finland. And let me see if I can. Technology, let's see. Can I get it into the YouTube app? Where's my YouTube app? Where's my YouTube app? Stay with me, guys. Stay with me for a second here. There's my YouTube app. Okay. And if I can get this. And this is also in the Scandinavian countries. It's known as the Festival of Lights. And come on, work. I'm pressing buttons, nothing is happening. Come on, work you. Can you guys see it?
Nope.
Nope. Okay, that didn't work. All right. Let me get out of it, and I'll just go with the regular screen share.
Okay, I'm in there now, and something's there. I clicked on YouTube.
Lucia. I Skandinavia er det noen tradisjon.
I'm almost done.
2 hours.
She's speaking Scandinavian and explaining the tradition. She will be singing shortly. She got a beautiful operatic voice. That is my holiday bonus. All right, guys. Everyone have a happy. Everyone have a happy holiday season. And I will see you guys next year. Now, if anyone does happen to want to have a hangout at any time between now and the end of the year, could be at any time. What are you doing, Yanni? What do you got there? Taking a picture. Ah, there you go. Okay. Well, I will see you guys next year, and once again, everyone have a happy holiday.
11 o'clock.
Happy holidays. See you later, everyone. Bye, Yanni. Bye, Ed.